Okay, good afternoon, everyone. I want to welcome you to another consulting class. Of course, today I'm actually going to showcase another study. We call this the boss study. I remember on Wednesday, I walked you through another study that we call the herbicide study. And of course, that gave you an opportunity to see how statistical techniques can actually be used to actualize objective. Today, we want to look at another study because when you are in a consulting role, you are definitely um, could have different kind of study a client can actually bring to you. So the question is how how prepared are you in ensuring that you translate the client's problem into statistical solution and eventually into the client solution. So I welcome you to the BOSS study. And what is the intention? I'm actually going to give you a study design. Okay. The client actually, if you take a look at what I have here, it's either the client, paid a visit and is seeking statistical input or insight on how to go about the study. Or maybe this come up under mock consulting, where um, we have artistic display of participants, that try to simulate real life consulting engagement in order for us to see whether they've been able to or maybe they understand what to do in a consulting role and stuff like that. So this could be a real study and this could be an hypothetical one. But whether a real study or a hypothetical one, we actually want to have a way to provide appropriate statistical strategy that work in ensuring their objective is fully actualized. In the study design, the client wants to know if the buses arrive later in the low-income neighborhood than the higher-income neighborhood. If you take a look at this, the client is interested in isolating the effects of neighborhood on bus late arrival time. Okay, that is the intention here. Now, when you take a look at this, the sampling that was done, they selected 8 bus stops. Okay, 8 bus stops. And in each, the A bus stop from the low income neighborhood and another 8 from the higher income neighborhood. Okay, that was a sampling and that was actually chosen randomly. Okay, 8 bus stops. Okay, now let me tell you this. In the United States, you know, um, the transportation system provide a ride for school or children, okay, from home to school. and from school back home. Okay, and of course, the children actually know a particular bus stop they're gonna go waiting for bus. So the intention here is we have seen situation whereby bus arrive late in some neighborhood, but the researcher here is interested in the role played by the income of the neighborhood. Okay, and that is the reason why they actually seeking for statistical help. Okay, in the data collection, okay, starting at 8 a.m., okay, the scheduled arrival time and the actual arrival time of the first 5 buses were recorded at the selected stops. Don't forget, I know I told you the other time, we're actually using they randomly select 8 bus stops from each neighborhood, whether high income neighborhood and the low income neighborhood, and on each bus stop we actually observe the schedule and the arrival time of the first 5 buses. Now, when you take a look at this stop ID, this is one of them, one of the stop, and this particular stop is actually from the low income neighborhood. We just want you to see, okay, the schedule time and the arrival time. If you take a look at the first one here, you're actually going to see the bus arrive, uh, you know, at 8:03, and it was scheduled to arrive at 8 a.m. If you go all the way, you're going to see one at 8:15 actually came at 8:20. The one at 8:45, scheduled for 8:45, came earlier. If you say that is 8:43, okay? I wanted to take note of that. And of course, the one for 9:30 came exactly 9:30, and the one for 10:30 came exactly 10:31. But let me tell you this is just one of the stop in the low income neighborhood. In the low income neighborhood, we got 8 stops. We also have 8 stop in the higher income neighborhood. Okay, I just wanted to pay attention to, the study design. Okay, now, now going into data processing, okay, going into data processing, the question is, what is the response variable here? Okay, now, if you want to answer a question on what the response variable is, the response variable is actually going to be talking about delay time, which is the difference between the schedule and the arrival time. Okay, I just wanted to take note of that. So the actual arrival time minus the schedule arrival time. Okay, that is the response. Now, another thing I wanted to pay attention to is because when you are acting in a consulting role, it is expected that you understand the nature of the response variable you are working with. Okay, we've already identified that here. Now, maybe you observe some buses arrive earlier than the scheduled time. Okay, when you take a look at the one of 8:43, it was scheduled to arrive at 8:45, but actually arrive at 8:43, which was earlier, right? Now the question is, should we exclude those values from the study? Okay. Now the question, the response to that is you shouldn't. Otherwise, you're actually going to create a bias, systematic bias. it has to be included in the study. Okay? So all observed differences, whether arrival is early or late, all has to be included in the study. Does that make sense? Okay. Another one said there was an accident near one of the bus stops. After the first three times were recorded, don't forget, we are picking 5 observations in each stop. Okay, maybe after you observe the first 3 and you realize that there was an external factor, okay, and of course the external factor could actually, it is actually going to prolong the arrival of the bus, right? Because like where there's an accident. So the next 2 were quite late. Okay. How should this observation be handled? This observation can probably be seen as an outlier, according to Benkamp in 1982. An outlier is a data point that is not consistent with the rest, and actually, we're going to say the arrival, there's possibility that the next 2 arrival time may be extremely high. Okay, because of the accident. Now, uh, a particular researcher may decide to say, okay, I'm going to remove them. Another researcher could say, okay, I'm going to tolerate them, but I'm actually going to use more robust model. A more robust model that can accommodate the presence of an outlier. Okay? So, like I said, the outlier cause here is as a result of the environmental factor accident that happened, and that was not related to the bus schedule. I just wanted to know that. Okay, now, whenever we actually have our data set, okay, or following the research design that we have, we are now going to be thinking in direction of data analysis. And of course, there's going to be a lot of techniques in statistics that will come to mind. If you take a look at this that come to mind, somebody can decide to say, okay, I'm actually going to use a 2-sample t-test. Now, the reason why there's a suggestion of 2-sample t-tests is because we are actually comparing the mean of late arrival time in 2 different entities, okay, low income neighborhood and higher income neighborhood. But before we can actually suggest a 2-sample t-test, we need to first look at our data set, our data architecture matters, okay? And not only that, we're also going to look at the assumptions underlying the use of a 2-sample t-test. We don't just apply statistical technique without putting into consideration assumptions underlying the use of them. Now, there's something I really want you to observe. Each stop in the study, okay, if you want to use 2-sample t-test, each stop in the study will be seen as an observation and is going to take 1 value. But don't forget, in each stop, how many observations do you have? 5. It's a repeated measure. Okay? Now, which means in general, how many observations are you going to have? 8. 8 because the 5 observation within a stop, you could find the average for each of that. And because of that, your sample size will be very, very small for you to use a two sample t-test. Okay. Another assumption violation is independence. Two sample t-test requires, if I'm actually comparing means in two population, the two groups or the two population have to be independent. But right now, these are not independent. If you look at stops, okay, if you look at stops, there's a kind of repeated observation within a particular stop. And because of that, we're not going to recommend two sample t-tests. Let me tell you this. If you use two sample t-tests on the data, there's possibility you're actually going to get a result, right? The result could be you reject the non-hypothesis or you fail to reject the non-hypothesis, but the fact that you are using inappropriate, technique, you are not likely going to get a good result, okay? You are not likely going to get a result that will stand a test of time. When the premise of an argument is wrong, so the conclusion. That's what I know. If you end up using a wrong technique, then your conclusion, is not going to be valid. Okay, now we have to think since there have been the takeaway from not using, the two sample t-test is because looking into data architecture, okay, there's actually a violation of independent assumptions. Two sample t-test is parametric test that rely on assumptions. Independent assumption is very, very crucial. The fact that you select the sample size randomly does not solve the problem of independence. Does that make sense? Now, because of the fact that, there's actually going to be, a specific, the bus stop will have their own specific variation. You know why a particular bus stop we have specific variation is because in a particular bus stop you observe more than one arrival. Don't forget we are observing 5. That's created a repeated measure. Now we know that going by the data architecture, repeated measure is involved. Then we need an appropriate statistical methodology that go with repeated measure. And that is what we call, repeated measure ANOVA that we call mixed effect model. Mixed effect model. In the mixed effect model, okay, we're actually going to have opportunity, okay, to capture variation in the bus stops. Okay, we'll be able to capture variation within a particular bus stop. Okay, now if I want to write a model, let me first do this. I'm actually going to do this. Do you know that this one? That would have been the model if we are assuming a two sample t-test. Do you know that two sample t-test is the same as you testing the effect of neighborhood on the late time? Because the neighborhood here is categorical variable. So when I'm testing the effect of neighborhood on the late time, if the regression coefficient associated with the neighborhood if the p-value associated with the regression coefficient is less than 0.05, you are actually trying to say, it is significant. Neighborhood effect is significant. Neighborhood effect, being significant, it is the same as saying there's a significant difference between the late arrival time for the two neighborhoods. But we've already said, I've already given you the reason why if you use that, it's not going to work. Okay. And that is the reason why we are now adding another component. And I need you to pay attention now. That is what make the whole thing to be a mixed effect model, because why is it a mixed effect? Because the neighborhood is fixed, then we are making stop to be random. Why are we making stop random? Because we want that random effect to capture variation within a particular stop. When there's going to be variation within a stop, because you have a period measure. Now, and that's what I'm trying to explain here. Okay, that's what I'm trying to explain here. Okay, I said the random intercept allow us to capture the inherent variability in the late time between different stops. Who doesn't understand that? Is there anyone who doesn't understand that? Let me explain each term. I need you to understand each term in the model. This one is represent the intercept. Okay, the intercept is going to be average arrival time. Okay, in all bus stops and in all neighborhood. Okay, average arrival time in all bus stops and in all neighborhoods. That is the intercept. Okay, now the neighborhood here, I'm actually talking about the parameter. For instance, if I want to rewrite the model in terms of parameter, this I need you to pay attention. In terms of parameter, let's say I write y equal, okay, beta naught. Please pay attention. Okay, plus beta 1. Okay, I'm taking my neighborhood to be x. Okay, plus. Okay, then maybe I have gamma j. Okay, the gamma j, or that I actually have. Then I'm finally going to have an error. Okay, I'm finally going to have an error. Now, let me be specific. If I put that j and put this one to be j, and I put the error to be aij, okay, obviously y is also going to be aij. Now, I need you to pay attention to what I'm showing now. There are two random components in this model. Of course, if you take a look at this one, this is a random component that is actually that capture the variability in stops, in bus stops. Okay, but the other one here, that is unexplained variation in a typical statistical model. There's always going to be a place of unexplained variation. So which means probably referring to some aspect of that cannot explain the delay in arrival time. Okay, now if you look at the way this is written, please pay attention. If you look at the way this is written, okay, this is like you actually nested the intercept in the stop, which is indicating random intercept. When you take a look at this model now, there are two intercepts in this model. Please pay attention. The first intercept is this guy. The second intercept is this guy. But the second intercept there is random. Does that make sense? And that is the explanation. The random intercept allow us to capture the inherent variability of course, in late time between different stops. Now, let me tell you this. Uh, we make the stop to be random, but the neighborhood is fixed. It's not random in the first one. Let me tell you this. The assumption in the random intercept is this: even though there's a variation in the bus stop, but effect of neighborhood is the same across bus stop. That is the assumption here. I'm going to say that again. Effect of neighborhood is the same across bus stop. That is what is making neighborhood to be fixed. When I say fixed, this is what I mean. Please pay attention. If you don't understand, ask me a question. Fixed. Okay? We believe the effect. We believe across, when I say the effect of neighborhood across bus stop is fixed, means is the same. It is synonymous, as saying like, they have the same slope. All bus stops have the same slope. Okay, which means in every bus stop relationship between the late arrival time and the neighborhood, the relationship is the same, more or less talking about parallelism. We could have another assumption that there is possibility. Please pay attention. We could decide to extend our mixed model to a possibility that, in addition to us having a bus stop specific variation, there is also possibility that the effect of neighborhood in different bus stop is not the same. If the effect of neighborhood in each bus stop, across bus stop, is not the same, then we also going to consider random slope. You can see now, random. So we are having, if you take a look at this now, this is like we are having both random intercept and slope. Take a look at this. One, okay, the intercept, that one represent the intercept and the slope. They are now being nested in the stop. Intercept and slope nested in a stop is to say that there's variation between stops. There is a heterogeneity in the bus stops. And not only that, effect of neighborhood on bus stop is not the same. Does that make sense? It's an assumption. This is an extended mix effect model. In this mix effect model, I'm considering random intercept and random slope. But in the first one, I'm only considering random intercept. I did not consider random slope. Is there anyone who doesn't understand that specification? Is there anyone who doesn't understand that? Okay, another thing I'm going to talk about. Please pay attention. If you don't understand, ask me a question. Another thing I'm actually going to talk about is this model, random intercept and random slope, can come in two forms. I'm going to say that again. Random, with situation where we have random intercept and random slope can come in two forms. When two terms are random in a model, I'm going to say that again. When two terms are random in a model, we got two possibilities. They could be correlating or not. Because of that, we can have this model in terms of a correlated, like where the random intercept and the random slope are correlating. And we're actually going to have another one where the random intercept and the random slope are not correlating. Now, if I want to, in the actual sense, when they are correlating, you know what I mean? When the random intercept and the random slope correlate, it means the higher the higher average maybe arrival time or the late time or delay. The higher average that can be, effect of that is different in different neighborhood. That's what I mean. We have a way to investigate all of that. We have a way to determine which model is the best at the end of the day. So what I'm trying to showcase today, this is mixed effect. We call this mixed effect models. They are models used when you have a repeated measures. Okay. Now, if I actually, maybe I want to indicate the other one. Please pay attention. I'm going to write something, out. Okay. Now, what I'm going to do is this. If I write late, okay, late time, okay, late time equal, okay, I'm having late time equal, oh, let me just say, sorry. Let me write it this way. Um, I'm gonna write, late time, okay, late time. Please pay attention to what I'm explaining. When I'm done, you're gonna see the way it's gonna look like. Late time on 1 plus neighborhood, okay, on 1 plus neighborhood, okay, 1 plus neighborhood, okay, plus 1 intersect nested in stop. I told you intersect nested in stop is a random intercept, okay, okay. Then I have, let me say I continue here, I say plus, okay, and I write the other one here, and I write is 0 plus neighborhood. Please pay attention. Is 0 plus neighborhood. I'm going to tell you what I'm writing down, okay. I'm going to tell you. So 0 plus neighborhood, okay, 0 plus neighborhood, okay, 0 plus neighborhood nested in stop. Please pay attention to this. Now, what am I trying to say? Okay, what am I trying to say? I'm going to tell you now. Okay, now, if you take a look at this, when I put 0 plus, then I'm talking about a random, a mixed model with a random intercept and random slope, and they are not correlated. Not correlated. You're gonna put 0 plus. But in the other one, okay, here is a correlated one. I'm assuming that this guy here, I'm assuming this one is for the correlated, where the random intercept is correlating with random slope. I told you, whenever you have two random in a model, they could be correlating or not. How many models do we have in general? We got 3 models now. We got 3 models. And let me tell you the simplest of the model here. The simplest of the model here is the random intercept model, where you have random intercepts and the slope is not random. Then the second simplest is the one where you have random intercept and random slope and they are not correlating. The third one is this guy. Does that make sense? Okay. And of course, I just told you that the random slope acknowledges that the effect of neighborhood or neighborhood income on late time may vary across stop, different slopes across stops. Okay, now you can see how many models do we have? We got 3 models. Can you see that? Now, if you want to fit, let's say for instance, you want to fit this model to the question at hand, you fit all of them. When you fit all of them, I'm actually going to call random intercept model 1. I'm going to call um, random intercept and slope where they are not correlating module 2, and I'm calling this guy module 3. How do I choose between two modules? Okay, all these modules are nested. They are nested. Then I'm going to use a nested ANOVA. Now the nested ANOVA in R, I'm just going to write ANOVA. Okay, in the code, I'm going to write ANOVA. Okay, in the parentheses, I'm actually going to put the simpler module of the two. For instance, if I'm comparing between M1, I compare between M1 and M2. Take a look at that. It means I actually want to compare module with random intercept only with module with random intercept and random slope, So, and after doing that, okay, let me say this. Let me say this. Give me 1 second. I'm actually going to say this. The way we start, you start with the random intercept only. Then from there, you go to random intercept and random slope. Let's say, for instance, you compare random intercept only with the random intercept and random slope. Let's say you reject the null hypothesis, because the null hypothesis is always going to favor the simpler model. The alternative will favor the complicated model. If you reject the simpler model and you are going for random intercept and random slope, then the next step is to investigate between two different kinds of model where the random intercept and random slope are not correlating and when they are correlating, to be able to decide. Okay, now let me tell you this. We have assumptions for each model, whether random intercept. Assumptions in the random intercept only, okay, is that the random the random component must follow normal distribution. And not only that, the error must also follow normal distribution. Please, I need you to pay attention. For random intercept, you need to first investigate whether the random intercept, assumptions underlying before I can compare modules. Before I can compare modules, the module on their own, this module, okay, must have obey assumptions underlying the use of the module. So what I'm trying to say is, for the random intercept module, assumption will be the random component follow normal distribution, the error follow normal distribution. How am I going to investigate if the random component follow normal distribution and the error follow normal distribution? I can construct a normal QQ plot. Normal QQ plot of residual will do the job. Does that make sense? The normal QQ plot of residual will do the job. Another assumption of a random intercept model is a constant variance. Constant variance. How the residual must have a constant variance. The error must have a constant variance. How am I going to investigate that? I will use residual plots. Residual plots can be used to investigate assumptions of constant variance. Now, for the random intercept model, we have additional assumption. From the random intercept and random slope model, assumptions, don't forget, two things are random. Okay, each of the random components must follow normal distribution. It means we have three things that will follow normal distribution. Okay, the coefficient associate the random component for slope must follow normal distribution. The random component for intercept must follow normal distribution. The error in the model must also follow normal distribution. How many? There are three. And assumptions of constant variance, two. Okay, I just wanted to take note of that. I used to do the statistics, our models are not failing us. Probably we're the one that we're not doing the right thing. Okay, now again, in the data analysis, the bus frequency vary from stop to stop, as we know. At some stop, 5 buses have already arrived by 9 a.m. At others, it's until 10 a.m. to record, the five arrivals. Now the question is, do we need to adjust for the frequency of buses? Okay. Now, I said something the other time. Okay. Even though there could be some external fault, external, factor that could make some buses to arrive late, that needs to be controlled. Okay. Now, and that is the reason, we will be considering matching. Here the other time I talked about matching. Okay. Now, depending on the analysis you're conducting, we can decide to adjust for bus frequency in the study design stage to be able to reduce the effect of variable that we did not, that potentially affect results. Let me tell you this. If we didn't do this, what I mentioned here, if we didn't do this, you know what is going to happen? It will tell on the error in the model. Every statistical model has an error component. If you don't do what you're supposed to do, it will fall back on the error, and the error will not behave well. Does that make sense? And that is why, so I said, adjusting for bus frequency in the study design stage, then make sure that both type of neighborhood have the same number of high frequency bus stop and low frequency bus stop. I mentioned this the other time. It's like, exposing, the two treatment to the same identical condition, so that we don't want situation whereby that if we don't control that, okay, it may be difficult for you to isolate the effect of neighborhood. Okay. Now, measuring the bus frequency and accounting for it in the analysis. Okay, if the bus frequency information for each stop was recorded, we could account for its effect on late time by including it in the model. Now, this is what I'm saying. Reason why we have a lot at times in our model is because we want to control some covariate that could potentially have effects on the relationship, even though we know the main variable of interest. Let me tell you this: the main variable of interest in this model is the neighborhood. That is the main variable of interest. Neighborhood income is the main variable of interest. But there could be other potential, maybe the condition of the, maybe the condition of the neighborhood, the condition of the road in the neighborhood, the weather, and so on like that. They all need to be included in our model. Included in our model, it means we are adjusting for covariates. We are controlling them. If you don't control them, they're actually going to have effect on the error. And whatever that have effect on the error, we have effect on the validity of the results. And that's exactly what we mean. Okay, in the discussion, suppose that the analysis shows significant results and the effect size is large enough, because let me tell you this, what makes statistical significance to be different from practical significance. In practical significance, we don't just focus on the p-value only, we focus on the effect size. Okay, now let's say here, you've rejected the null hypothesis and the effect size is big enough. The question now, are there any problems with generalizing the result of this study to show that in general, not just in the selected routes, buses arrive later in a lower income neighborhood than in the higher income neighborhood? Okay, so what we're trying to say is we have to put into consideration before your results can be generalized. Then you must have done a very great job of controlling for some factors that are called external factors that could influence relationship. Okay, I mentioned there are the stops selected randomly. I need to ask that question. The way they select the stop initially from the lower income neighborhood and the higher income neighborhood, do they use principle of randomization? That is one. Number two, Data, do they collect data on only one day only? Because difference in days could actually potentially influence the outcome. And also I said, I said cannot generalize to other days or weather, because for instance, if I only base my decision on one day, there's possibility because of difference in days, I may not be able to generalize the result on the other days. That's what we mean. Okay. Or maybe I conducted that during the summer. Okay. I cannot generalize for winter. That's what it means. Cannot generalize to other seasons as well. So we got to be careful. Now, data collected between 8 and 10 a.m. Okay, we cannot generalize to other time of the day or night or nighttime. Your generalization will only be for, it's going to be between 8 and 10 a.m. because your study focus on 8 to 10 a.m. Okay. Now, discussion continue. The client has some hypotheses about possible reasons for buses arriving later in the low income neighborhood. Okay. And the reasons could be, these reasons are those ones that you need to control. Older buses, maybe the bus, okay, that apply the routes of the low income neighborhood, maybe if you look at the lifetime, maybe they are old. And that is why maybe they are, that is what slowed them down. Worse road conditions, more road closures. Okay. So there could be other potential factors. Okay. Now the statisticians should have a way for testing them. They have to be included in the model. Because before I can actually conclude that significant difference exists or the neighborhood as income as effect, then I must have done a great job adjusting for other covariates. Okay. And let me tell you this. If we actually conduct an experimental study where we follow the principle of experimental design, okay, there's possibility whatever bias would have been averaged out. But if you're not able to go for experimental study, you go for observational study, okay, there's a way we can also control stuff like that in observational study by way of matching. Okay. So by way of matching, we mean the route that I'm considering in the low income neighborhood should also be the same road I'm considering in the higher income neighborhood. It's more or less like matching them up, making sure they are in the same identical condition. And that was why I said, suppose we want to study if road condition caused the delay, randomly select some bus stop with poor road conditions. Note the condition of the buses on this route, the type of the neighborhood, and any other kind of condition. Find similar bus stop that match up except that they have better road conditions. Okay? And finally, I said, you measure this condition and you adjust for the condition in the analysis. Without doing that, it's an exercise in futility. It's actually going to look as if our models are failing us, our models are not failing us, but we don't know, at times we don't do the right thing. Doing the right thing is paying attention, making sure, understanding the data architecture, understanding the assumptions underlying the use of your model, and at the end of the day, you're actually going to have a valid result and a result that will stand a test of time, a result that can be generalized. This is where I stop. I'm actually going to stop today. I attached a material on repeated ANOVA. I'm actually going to walk you through in case you want to conduct repeated and the repeated measure in R. Okay, I've already attached a material on the canvas, and if I have time, I'm actually going to go over that material with you. This is where I'm actually going to stop. It's another weekend. Make sure you all stay safe and have a lovely day. Bye for now, everyone.